Let me share my screen. So this is going to be the agenda for the last and final session on this workshop. We briefly talked about decision trees yesterday. We couldn't complete it. So let me complete the concept of decision trees, the CART algorithm that we have seen. We didn't talk about the advantages of trees and then some of the challenges that we face when we use tree-based algorithms. That would complete the decision tree. Then we move on to unsupervised learning, where we would see an unsupervised learning algorithm called k-means algorithm. And through k-means, we are going to perform clustering. And maybe I'll keep 10 minutes at the end of the session to briefly talk about what are the next steps and what are the other types of algorithms and what's the algorithms that you typically see in artificial intelligence and why they are different, so that anyone who is willing to explore them on their own, they would be able to at least have a list of a handful of algorithms so that they can start learning them on their own. So with that, let's jump into our discussion today. So we talked about what a decision tree is, what a decision tree does. We start with all the observation at the root node. So this is our root node. This is our sample training data. Let's say we start with those 1,000 observations that we have. 1,000 observations is 70% belong to no class and 30% of them belongs to S class. And that's the separation at the root node. Let's say at the root node, we computed the Gini value. Either we can use Gini or we can use entropy, doesn't really matter. Let's say the Gini is 0.4 here. Gini will be close to 0.5 if impure. So here it is 70-30, which is not purely impure. So let's say it's approximately around 0.4. We have input variables x1, x2, x3, x4. Now within x1, let's say x1 is taking values from 0 to 20. That's the range. Minimum value is 20, minimum value is 0, maximum value in x1 is 20. Now we create split points in x1 like this. Let's say we create split points based on 25th percentile. Then it would be x1 less than 5, x1 less than 10, x1 less than 15. That's the 3 split points that we have in x1. Let's talk about another variable x2. x2 is having values, let's say, between 50 to 60. x2 is a different variable and x1 is a different variable. So we have values between 50 to 60. Now in x2, I have split points like this. Let's say x2 less than 52, x2 less than 54, x2 less than 56, x2 less than 58. So these are the split points that we choose in the variable x2, and these are the split points that we choose in the variable x1. Now, for this split point, if we separate the data based on this x1 less than 5, we got, let's say, some 800 observations here and 200 observations here, and this is based on x1 less than or equal to 5. x1 and less than or equal to 5 gave a Gini of 0.1, This one gave a Gini of 0.2. This one gave a Gini of 0.3. Which one is best? The one that is having the least value of Gini is the best one. So within x1, we choose this as our split. On x2, let's say we got a Gini of 0.18 here, 0.12 here, 0.08 here, and 0.2 here. So within x2, what is the best one? So this is the best one. So this is the best available in x2. Now, if you try to compare between x1 and x2, x2 less than 56 is giving you 0.08. x1 less than 5 is giving 0.1. Among these two, x2 is the best. So we would probably try to divide the data at the root node using the variable x2. So the first root node split is based on x2 less than 56. Why? This is the one out of all the variables that is giving you the maximum decrease in Gini, and that's why we are using that variable to split the data. Now this become another parent node. We can split this further, and this become another parent node on the right hand side. So this will be divided further. So we keep splitting this data using different split criteria. Let's say we use x3 here. Again, we can use x2 here. Why? In x2, less than 56, yes is this side, greater than or equal to 56, yes is this side, no is this side. So all the observations which has values greater than 50, less than 56 is this side. All the observations which has x2 greater than 56 is this side. We have one more split point here. If this can split this data, again we can reuse, okay, the same variable. And this will stop at one point where conditions are all observations are separated. That means in the leaf nodes, we have observations like 0, 100, 200, 0, 100, 0, sorry, 200, 0, something like this. All 1000 observations are perfectly split, and at leaf node, either we have observations that belong to S category or no category. Either we have observations that belong to S category or no category. So this becomes our leaf nodes. So if this is achieved, it would stop. But perfectly separating them is not possible in most of the cases, right? Now, if it is perfectly not separable, second condition is no decrease in Gini. For example, here, this is a parent node. Let's assume this is a parent node. We try to split this further into two small nodes. None of the splits that we choose is able to decrease the Gini. So here the Gini is 0.1. We want to decrease this further, but none of the splits was able to decrease the Gini further, so it would stop. So if any of these two conditions is met, the decision tree will stop. And this is the learning phase. We have got a data and we started to separate them in such a way that the separation between the S and no observations keep improving until a point where they are all separated, or there is no way that we can decrease the Gini further. Same case with entropy, but entropy is not used. If you remember, entropy uses log to the base 2, computationally heavy. So instead of entropy, Gini is more preferred. So I'm using the Gini example. Now, we have already built a decision tree in Python, and then we looked at the decision tree and how it has performed on the test data, we got 100% accuracy, right? What happened here is we gave all our test observations to this tree process. Let's take one test observation. You have all input variables, x1, x2, x3, x4. First, is x2 value less than 56 for this observation, test observation? Let's say it is true. Now it comes here. It falls into this particular node. Next, x3 less than 10. Let's say this is the next condition. If it is true, this side. If it is false, this side. And finally, it reaches to a stage where it lands into one of the leaf node. Let's say it landed into this leaf node, and in this leaf node, all the observations are, majority of the observations belongs to S category. So we predict them, we predict this observation should also belong to the S category, right? That's how a decision tree works. And decision trees are very simple and easy to understand compared to linear logistic regression, where you have some mathematical calculations, where you have other complexities. Here it is just like how our brain thinks. Human brain is naturally um, built for linear thinking, like this type of things. Like, okay, if something is true, this side. If something is not true, this side. So we process the data using some sort of if-else conditions like this. So if we have to separate something, we try to compare them. So if someone keeps a mango and apple in front of you, how do you decide which one is mango and which one is apple? That's probably by processing some sort of if-else rules like this. If it is pinkish in color, red in color, maybe it is an apple. If it is yellow in color or saffron in color, maybe it is an apple. So this is how, sorry, mango, this is how you process. That's exactly how decision trees are also trying to process and take decisions based on that. Good. The advantages of decision tree is we don't have to do any sort of pre-processing. You get the data, you clean the data a little bit, you dump the data to a decision tree algorithm, it learns, and through that learning, it can make predictions. In linear logistic regression, we have to deal with a lot of challenges. Some of the challenges, checking if target variable and input variable is related or not. Second, if the relation is strong or not. If there is no relation, omit those variables. If there is relationship between target variable and input variable, take them. So these type of decisions have to be taken by us. What variables should be used to predict the target variable Y is decided by the data science developer in case of linear logistic regression. But when it comes to decision tree, you don't have to do all these things. You don't even have to do EDA for that matter. You dump all the variables to the decision tree, and decision trees try to learn from this data and make very good predictions out of it. In a way, it reduces a lot of effort of a developer. Computationally, linear logistic regression is much easier, but decision trees are very tough. Imagine if you have 100 variables, for all the 100 variables, it has to identify the split points, compute the Gini for each of them, and do it for all 100 variables, pick the best one out of it to separate the first split itself. So much amount of computations happens behind the scenes, but it's a CPU problem. We don't have to worry about it. If CPUs are powerful, they are definitely capable of handling all these processings in maybe a matter of a split second. So they don't really take much time. Next, coming to the challenges, of course, every algorithm will have advantages and disadvantages. Advantage of decision tree is simplicity. You don't need to be a data scientist to understand this. How are we coming up with a prediction? Using simple if-else rules. If x2 less than 56, then if x3 less than 10, then if x4 greater than something, it comes here. I am predicting it as S. So it's a simple nested if-else rules that is actually making the prediction. So anybody can easily understand. Next, you don't have to do the variable selection. You dump all the variables and decision tree is able to learn from the variables on its own. Then what are the disadvantages? So the disadvantage for a decision tree is overfitting. So this is definitely a very heavy concept. I will try to give a simple example of overfitting. Overfitting is learning too much from the data. Indirectly, it is like memorizing the data. When you memorize the data, what happens? On the exact same data, you perform very good. So if you try to memorize everything in the textbook, same examples come in the exam paper, you do a good job. But if you don't put a logic to it, if you just try to remember, in the exam, if the examples are similar but with a different data, you may not be able to do a good job. So that's simply what we call as overfitting. Overfitting is doing a very good job on the learning data and not so good on unseen data, on test data. So decision trees are highly prone to overfitting. They generally keep learning until they try to separate all of them. So naturally they will try to overfit. To overcome this problem of overfitting, we have a technique called as pruning. So what is pruning? Generally, if you are growing a tree in your garden, if the tree overgrows than what you expect it to be, and it becomes a problem for you, you cut some of the branches of that tree, right? You are not going to cut the entire tree out, but at least if you take some of the branches out, it would still remain. So that's exactly what we call as pruning. So we can prune the tree using a lot of these conditions. Imagine here, decision tree classifier. These are all the arguments that this decision tree classifier can take, but we haven't used any of them. We just left it to the default values. But if we think that the tree that we have built is overfitting, then we need to prune the tree using some of these parameters, some of these arguments that we have here. The most commonly used one is maximum depth. So a max depth of a tree is measured like this. It is based on, in a simple terms, you could use this as the depth of the tree. What is the length of number of splits from the root node to the lengthiest leaf node? Let's say if we take this as the lengthiest leaf node of this tree, 1, 2, 3, 4, 5. So 5 decisions or 5 splits are used to reach the lengthiest leaf node of the tree. Maybe we can call this as the maximum depth of the tree is 5. So by default, maximum depth of the tree is given as none. So we are not giving any criteria. We can give a criteria. If we say maximum depth is equal to max underscore depth is equal to 4. Now we are explicitly overwriting the decision tree algorithm saying the tree can learn up to a maximum depth of 4. The moment it touches 4, stop learning. Don't do. Even if it is possible, don't do. Now, indirectly what we are trying to do to the tree is we are cutting all these branches out, and when you cut these branches out, this one here will become the leaf nodes. So pruning is taking some of the branches of the tree out, which is leading the tree to overfitting. Yeah, but you need to read a lot about this topic. Simple way is we do not want the trees to overgrow so that they become a problem for us. We want to stop the tree from learning further when one of these criteria are met, and the most commonly used criteria is max depth. Okay, so that's the disadvantage of the tree, and to overcome that disadvantage of the tree we use this maximum depth. Okay, we can also use maximum leaf nodes. We can also use minimum number of samples to split. A lot of them. Each one of them has their own way of working. So if you have to understand what each of these parameters does here, then you have to go deep dive into behind the scenes how algorithm is working, how algorithm is making decisions, etc. For now, if you think overgrowing a tree is leading to overfitting, we can control the overgrowing of the tree using this parameter max depth. If you don't give anything, the tree will continue to learn as long as it is possible. But if you restrict the maximum depth to a particular number, it would stop there. Even if there is a possibility to learn further, it won't. It would stop there. Okay, so that's all we have on the decision tree. Let me check if there are any questions. Then we can move on to the next topic. Alpha beta pruning is based on something called as the cost of complexity. Unless you understand the cost of complexity, you see here CCP underscore alpha is equal to 0.0. We did not give anything. But if you understand first how the cost of complexity is calculated, then you will understand that. That's slightly more depth concept, would take easily another 30-40 minutes to explain. Not required for a beginner. It's not totally random. You have 4 input variables, right? Now, out of the 4 input variables we have, in each input variable, we identified the split points. How did we identify the split points? Let's take 10th percentiles. Every 10th percentile is a split point for us. So the split points that are available here in x1, the split points that are available in x2. For each split point, we computed what would be the Gini value. We choose the one that has the least value of the Gini, and we compared them across variables. Whichever variable gave the least value of Gini at a given split point, that one is made to make the first split. Now this becomes a parent node, this becomes another parent node, same process. For this node, what are the available variables? What are the available split points? Try to check which one gives the least value of Gini at the child nodes. That would be choose to make the split. That would be continued until one of these 2 criteria are satisfied, or a third criteria which I just mentioned, like force stopping the tree from growing using a max depth. If that condition is satisfied, one of these conditions satisfied, the tree will stop learning. Okay, with that, let's move to our next topic called unsupervised learning clustering. What do you mean by based on the random variable we can construct a decision tree? It's not based on a random variable. We have 4 input variables, and from these 4 input variables, we are checking which one can separate the observations between S and no class to the maximum extent, and based on that variable we are making the split. Okay, trees doesn't have to be symmetric in nature. This is another good point. So don't expect that trees should be always like the symmetric tree that I have shown. Now if we try to split this, let's say we got a left hand child and we got right hand child. Left hand child is divided further into multiple smaller subsets, but on the right hand child we were not able to split this any further, so this becomes a leaf node by itself. So if we cannot split anything further, so that's a leaf node. So if you want to represent that in a more easy form, this resulted in a leaf node directly, so that's a leaf node for us. On this side we have more splits that's happening, and this one resulted in a leaf node directly, so this is another leaf node for us. And this one is going to split further, so this one got a leaf node for us, this one generated a leaf node for us. This is split again further into two, so this is going to split further, so you got a leaf node. If this is an example of unsymmetric tree. Okay, on the left hand side we made a lot of splits to reach the leaf nodes, but on the right hand side the first split itself is resulting in a leaf node, because you could not split this any further. If an observation comes here and it reaches here, whatever is the majority class here, that would make the decision at this leaf node. Yeah, don't expect that this is a tree like what you typically see in data structures where you have a lot of symmetric shape. No, the trees can be very much asymmetric. And jumping on to the clustering, let me quickly complete the theory part of clustering also before we see the example. Here there is nothing like a prediction, so you don't have to see the example first. If you understand the logic of it, it is good enough. So you have only input variables x1, x2, x3, x4. Let's say these are our input variables. These are the 4 input variables that we have. There is no target variable. So this is unsupervised learning for us. So in unsupervised learning, we would not have any type of target variable. So what we want to do is, let's say we have observations 1, 2, 3, all the way up to 1000. For these observations, we have to create a new variable. Let's say we call that as cluster. Observation number 1 belongs to cluster 2. Observation number 2 belongs to cluster 3. Observation number 3 cluster belong to 1. 4 again 3, 2. So we are trying to build 3 clusters here. Each observation would be assigned to a particular cluster. Like here, this observation is assigned to cluster 2. This observation 3, again some observation 2. So these 1000 observations would be assigned to one of these clusters. And here we are going with the clusters, number of clusters, k is equal to 3. So that's why we have built these many clusters over here. Now let's start with what is the science behind this clustering and how to do it. One of the most popular technique for clustering is k-means. The k here is nothing but the number of clusters that we are going to generate. So that is why the algorithm is named as k-means algorithm. So what happens in a k-means algorithm? Like this. Let's say we have x1 and x2. Both are input variables. So in this case, there is no target variable. So we are just trying to represent them in the form of x1 and x2. Let's say x1 is years of experience and x2 is salary. Now let's say this is the information of some employees. So using the years of experience and salary, we want to divide them into some clusters, some groups. Okay, let's see how to do it. Now we have observations like this. So these are our observations typically. Okay, now we want to group these observations into, let's say, 3 groups. What could those 3 groups look like in a best case, in an ideal case? Remember, when we are trying to divide them into clusters, we want the clusters like this. Within the cluster, all the groups has to be similar. Within cluster, all the observations has to be similar. We call this as homogeneity. Within a cluster, all these observations are very similar. They should exhibit similar characteristics. Across the clusters, that means from one cluster to another cluster, they have to be heterogeneous. That means an observation that is present in one cluster and another observation which is present in a different cluster, they have to be very different from each other. That is when probably we could say the clusters that we have created are really good. So it has to satisfy these 2 conditions. So within cluster, homogeneous, across cluster, heterogeneous. So let me try to visually show you how could the clusters look like. Let's say, for example, here, if we group all these observations together and these observations together and these observations together. Don't you think these observations that are grouped together in different colors, they are very near to each other? We think that they are very similar to each other. So we wanted to create 3 clusters. Let's say this is cluster number 1. Okay, this is cluster number 1, and this is cluster number 2 here, and this is cluster number 3 here. At the beginning, we had all the observations together. Then we try to separate those observations into 3 clusters that satisfies this condition. Within the cluster, they have to be very similar. That means all the observations that look very similar to each other falls in the same cluster. Observations that look very different from each other, they fall into different cluster. This is exactly what we call as clustering. To make the visualization easy, I am only using a 2-dimensional one over here. I'm not using one more variable. Let's say if we use one more variable, it becomes 3-dimensional and it's very difficult to visualize it. So let's say for now, we are assuming that we have only 2 variables, 2 dimensions, and using those 2 dimensions, we are generating the clusters. But in practicality, we would have a lot of variables as input variables, and we generate the clusters in a multi-dimensional space. A multi-dimensional space is very difficult to imagine for a linear thinking human brain, so we would not touch upon how does that multi-dimensional space look like. So if we understand this with a two-dimensional space, then we could easily replicate this to a multi-dimensional space. Yeah. It's not grouping the variables, it is grouping the observations. Okay, how we do it, let's wait for it. I'm just trying to explain the objective of clustering. Objective of clustering is we have observations. So these are our observations, and I plotted the observations on a two-dimensional space, x1 and x2. I want to group those observations which are similar, which are near to each other in a way, in one group. So these observations which are very close to each other, they are grouped into one. These observations that are near to each other, they are grouped into a separate group. These observations that are grouped to near to each other, grouped into another group. Here, because we choose to go with k is equal to 3, our clusters look like this. If we choose a different value of cluster, so if we take 4, maybe the clusters would be very different. It would look very different from what you are actually seeing here. Okay, so first step in a k-means clustering is we need to decide the value of k, how many clusters we are trying to form. And how to choose this value of k? Yes, we do have analysis for that as well. But let's first understand how the k-means algorithm grouped these observations. Don't use the term grouping the variables. We are not actually grouping the variables here. We are actually grouping the observations. We are grouping the observations based on the variables x1 and x2. And how do we do that? How do we call two observations similar to each other if they exhibit same characteristics? Look at these two observations here. In terms of both years of experience and salary, they are very close to each other. So we can call these two observations as very similar to each other. So to say if two observations are similar or two observations are different, how similar they are or how different they are, we need a metric. The types of metrics that we use when we are looking at similarity between the observations, there are two types of metrics that we generally use. One is a distance-based metric. The other one is a similarity-based metric. I'm not going to talk about similarity-based metrics here because it would take a lot of time and we need to understand other concepts also. But to give you an example of a similarity, the commonly used similarity metric is called as cosine similarity. Then the distance-based metric, the commonly used distance-based metric is Euclidean distance. So if we have two observations in a two-dimensional space, a Euclidean distance is nothing but the shortest distance between those two observations, which is also called as displacement in physics. So to see how similar these two observations are, we use this Euclidean distance. So if this observation is x1 comma y1 and this observation is x2 comma y2, what is the distance between these two observations is measured using d is equal to square root of x2 minus x1 whole square plus y2 minus y1 whole square. Okay, that's how we try to measure the similarity. To give you a brief about this is Euclidean distance. To give you a brief description of how it would look like if we have to use the cosine similarity, uh, this is how we generally measure the cosine similarity. So on a two-dimensional space, you have an observation here. This is your x1 comma y1, and this is another observation here, which is x2 comma y2. To find out how similar these observations are, we try to find out the angle that separates these two observations. This is theta. So which is going to be computed as cos of that angle theta is going to be the similarity. Irrespective of their magnitude, if let's say if they are on the same line, they would be considered as similar. If they are separated like this, they would be considered as different. So this is called as cosine similarity. So that's why I said, if we have to thrive on in data science, of course we need to have a lot of our basic mathematics concepts. You do not have to solve them by hand. You don't have to remember, hey, how do I compute cos theta? What would be the cos theta values? Those things are taken care by programming languages like R, Python. A lot of people worry about mathematics and they hate mathematics for the reason they have to compute all those things by themselves. That's the biggest scare people have when it comes to mathematics. But if you tell them, hey, you just understand the concept, you don't have to compute them manually by yourself, mathematics becomes maybe 100 times easier, right? So here in data science, we need to understand all the concepts of mathematics and how we try to learn mathematics in our basic schooling up to colleges. But you probably don't have to hand calculate any one of this. So if you have 2 points, if you give the 2 points to a function built into Python, it tries to compute the cosine similarity for you automatically. But if you have to understand what is the cosine similarity, this is how you try to visualize it. If what is the difference between these two? We call them as vectors. What is the difference between these two vectors in terms of their angle? Now, if the angle is small, those two vectors are very similar. If the angle is very different, those two vectors are very different from each other. Okay, fine. Let's leave that. Let's come back to the k-means algorithm. If we want to know how similar an observation is with another observation, we can use this distance metric, which is the Euclidean distance. Now, with that knowledge, let's try to understand how we can generate our clusters using the k-means algorithm. I am plotting some points over here. This would look slightly different than the points that we have used already. So this is our x1 and this is our x2 variable. You decide the value of k. K is equal to 3. I have decided the value of k as 3. Once you decided the value of k is equal to 3, you need to choose randomly 3 points in this two-dimensional space. Because we are using two-dimensional, we are going to randomly choose 3 points in this two-dimensional space. If you are using more than 3 dimensions, 2 dimensions, then you would choose random points based on the number of dimensions that you have. Now let's say I choose my random 3 points like this. I'm just placing them without even looking at them, and that's what is all about randomness. So if I try to place them by computing something, that's not random anymore. So I randomly choose 3 points. This red point over here, this blue point over here, and then this green point over here. This is not original data. These are the points that are chosen by us. Now, once we place these random 3 points, we are going to compute the distance from each point to each centroids. We call this as centroid. So this is, let's say, C1, this is C2, and this is C3. The points that we have placed randomly are the centroids. So for this point over here, the distance between this point to this centroid is this. The distance between this point to this centroid is this. And the distance between this point to this centroid is this. Now, out of the three, which centroid is nearest to this particular observation in in question here? So this observation is nearest to centroid 2. So we would assign this observation to centroid 2. Now we do this process for each and every observation, and for this observation, this is the nearest centroid. For this observation, this is the nearest centroid. So we compute the distance from each observation to each centroid. Whichever is the least distance among them, we assign those observations to that particular centroids. Now let's say we assign each of these observations based on how near they are to different centroids. So for this one, the nearest ones could be all of these ones over here. So these are the ones that are nearest to the green centroid. For the red one, the observations that are nearest to the red centroid is maybe these ones. So this is the red one. And for the blue one, because it's completely kept out of our space, as of now, it has only these two observations. Okay. So this is iteration number 1. So this is step 1. So what is step 1? Let's write the step 1. In step 1, first randomly choose k centroids, compute distance from each observation to each centroids, whichever is the least, assign that observation to that centroid. My handwriting becomes poor if I write fast. Please bear with me. Now, our iteration step number 1 is done. So iteration 1 is completed. Now, doesn't our clusters doesn't really look good. Here, it's this centroid is absolutely far from the rest of the observations. You have only 2 observations in this, and they doesn't have a good shape. Now, once this assignment is done, we are going to remove these centroids, and okay, we lost some observations also with that. Let's try to put those observations. So there was an observation here, there was an observation here, this observation was there, this observation was there, this was there, and this was also there. Okay, to complete them. So what we did now is we removed those centroids. Whatever the centroids that we have placed randomly, we removed those centroids. Now from these observations, we are going to compute the new centroid, the new mean of this. So if you take all these observations, where would be the mean? The mean for these observations could be somewhat over here. this observation would drag the mean slightly towards this. For these observations, the mean would be somewhat over here. Let me place a dark circle. So that's the mean. And for these two observations, our blue centroid was here. Now our centroid would move exactly between those 2 points, right? So our centroids has changed their positions. Once the centroid changed positions, repeat step number 1 only from here. We don't randomly choose the centroids anymore. We are going to compute the distance from each centroid to each point. Whichever is the nearest, we would assign that to the new centroids. Now with that, let's say this observation here became more nearer to the green observation than the red one. Now your change of cluster would look something like this. So this observation entered this particular cluster. The red one changed like this. The red one changed like this. This observation, which was more closer to this observation before, might change to either blue if at all. And this type of computing the centroids, trying to see if there is any observation changing the centroid till we get to our final centroids, which would probably somewhat over here. The red one would be somewhat over here, and the blue one would be somewhat over. Here, and the final centroids are going to look like this. These observations are going to fall into the blue ones. These observations are going to fall into the green ones, and these observations would remain in the red ones. And no more observations change from one centroid to another centroid. This algorithm stops. So step 1, randomly choose k centroids, compute the distance from each centroid with each point, assign the point to the centroid. Once the step 1 is done, remove the centroids, compute the new centroids. So let's write those points from step 2. In step 2, compute new centroids, repeat. Let's say this is step A and step B. Repeat step A and step B until no observation changes the groups. Stop. And that's when you get your final clusters, which are going to look like this. So this is going to be your final set of clusters. So this is another cluster, and this is the green cluster, which is the final set of clusters. Okay. That's how our clusters will form. Step 1, start randomly some k centroids, compute the distance from one centroid to each of these observations, assign the observation to the centroid which has the least distance. Step 1 is done. Remove the centroids, compute the new centroids, and repeat this step until your centroids are not going to move. That means no observations changes the centroids from one group to another group. That's when your clustering algorithm has learned and finally stops. And that is what probably would result something like this. See, centroids, the reason why we are choosing centroids is you don't know how many groups exist in the first place. It could be 3, it could be 4, it could be 5, so on. So you need some sort of logic to come up with what would be the number of ideal groups to go with, and you need to iterate around them. So where would you place those groups? What would be the shape of those groups? Nobody knows. So to make that shape virtually learn from the data, we are choosing the centroids, finding the distance between the centroid and each observation. Based on the distance, we are assigning them to a particular group. Now, if you don't choose that, how could you form these type of shapes? Not possible at all, right? So we are choosing the centroids and using the distance between one observation with the rest with the centroids, we are trying to arrange them into clusters. Okay, now it doesn't stop there. We still have not answered one question. So that question that we have to answer is, how many number of clusters? What should be the value of k? So this is a tough question to answer. Generally, we need to have a bit of domain knowledge, and we also need to understand the client requirements. Say, for example, that bank, if the bank is very clear that they can easily manage the customers in 4 tiers, then it is good to go with 4 tiers. Sometimes they may not have any clue. Hey, I don't know how many groups are good to go with. You tell me what is the ideal number of groups to go with. So you need to choose the value of k. So to choose the value of k, we have to take a help from a graph, which is called as the spree graph. So the spree graph will help you to understand what is the ideal number of clusters to go with. The spree graph is generally constructed like this. The clusters on x-axis like this. What's the number of clusters? We try to construct the clusters like 2, 3, 4, 5, all the way up to, let's say, 15. And for each clusters, when clusters number is 2, 3, 4, 5, we compute a metric called as WSS. It's called as within sum of squares. Slightly difficult one to explain. Unless you have a thorough knowledge on statistics, you would not be able to understand this. So I would not go detail into this, but make a note of it. Once you get a good understanding of your statistics, then you would know how this within sum of squares is computed would look like. So this graph would look something like this. When clusters is 1, your within sum of squares value is high. 2, it decreases. 3, it decreases. 4, it decreases. 5, it decreases, so on. If you see here, when the cluster numbers are increasing from, let's say, 2 to 4, your within sum of squares is drastically decreasing. But after some point, let's say after 5 clusters here, it almost gets flattened out. So that means increasing the number of clusters any further is not going to make a better separation between the clusters. So wherever this graph gets flattened out, that's probably is the ideal number of clusters to go with. So we use this spree graph. It's also called as elbow curve. Technical name is spree graph, but non-technical name is elbow curve. So using this graph, we can decide what is the ideal number of clusters to go with. That means we are going to run k-means in a loop starting from, let's say, k is equal to 2 and all the way up to, let's say, k is equal to 15. So we are generating 2 clusters, 3 clusters, 4, 5, so on. When we keep generating the clusters, how is the variance within each cluster decreasing? If the variance in each cluster is decreasing, that's good. At some point in time, it almost gets stabilized. It doesn't decrease any further. And that's where you see this is the ideal number of clusters to go with. Looks like some questions came in. Let's see what those questions are. Okay, it's not about questions, it's about, yeah, I already explained why we choose centroids. And then, okay, looks like good. We are all set. Now let's jump into the exercise. And just like how we do, I'm also always going to take a fresh notebook, and we are going to add cluster, or you can rename this as clustering underscore k-means. There are a lot of clustering algorithms. You have hierarchical cluster, you have k-means cluster, and then you have k-modes, you have db-scan, and then you have most advanced clustering techniques coming in, right? But k-means is probably the most important one to start with compared to others. That's the reason I'm covering with k-means. But don't think that clustering is can only be done with k-means. Not all the time. There will be different types of algorithms that we can use. One more point that I forgot. It's very, very important for using k-means. Whenever we are using any distance-based metrics, so see here, we are using Euclidean distance. So how are we computing the distance from each centroid to the observation? Euclideans. So whenever we are using any distance or similarity metrics, we need to normalize the data. So what is normalization? So x1, x2, x3, x4, let's say x1 is salary and x2 is age and x3 is years of experience. Salary will be typically in lakhs, like let's say 20 lakhs is the salary, 25 lakhs per year. So these are in typically lakhs. Age, let's say 30, 32, so on. Years of experience could be 5 years, 6 years, or 7 years, so on, right? Now, when you compute the distance between these two observations, how do you compute the distance between these two observations? So 25 lakhs minus 20 lakhs, so that is on this dimension, whole square, plus 32 minus 30 whole square, plus 7 minus 5 whole square, and you take the square root of this. So this is the Euclidean distance between these two observations. Now, if you look at this, this is almost like 5 lakh square plus 2 square plus 2 square. For 5 lakh square, if you add another 8 to it, will it make any difference? No. The variables x2 and x4 being on a smaller scale has no effect on distance. Your distance is completely dominated by x1 alone. But still, age and years of experience is also important. So when variables are on a different scale, Euclidean distance doesn't really work well. So that's where we have to use a normalization. There are many types of normalization, but the most popular technique to normalize the data is using a min-max normalization. Let's see how does this min-max normalization work. Min-max value is xi minus minimum of x divided by max of x minus minimum of x. Let's say we have values like 10, 20, 30, 40. Minimum value is 10, maximum value is 40. So now if you convert this into min-max values, for 10, it is 10 minus 10 divided by 40 minus 10, which is 0. 20 minus 10 divided by 40 minus 10. So that's like 10 divided by 30. 30 minus 10 divided by 40 minus 10. So this is 20 divided by 30, and 40 minus 10 divided by 40 minus 40. So that's like 30 divided by 30. So this is 0, this is 0 0.33, this is 0 0.66, now this is 0. Sorry, this is 1. So in a min-max normalization, doesn't matter how the original values look like, the min-max values would always be between 0 to 1. Now here, if we try to change this into min-max, let's say these two observations will become like this. For salary, it is 0.25 and this is 0.3. For age, this is 0.28 and this is 0.32. And for years of experience, this is 0.25 and this is 0.28. Now, the scale is completely taken out, and this is called as descaled data. All of them are on common scale. Now, if you compute the distance on this descaled data, this could be 0.3 minus 0.25 whole square plus 0.32 minus 0.28 whole square plus 0.28 minus 0.25 whole square. Now, all of them are given equal importance over here. Salary, age, years of experience. So whenever we are using any type of distance-based metrics, normalizing the data, taking the scale out of the equation is very important. Okay, let's see what the questions are. K-means is computationally the easiest one out of all of them. Why? The computation is linear in K-means because you are using a Euclidean function, which is just like any arithmetic equation. So the computations of these type of ones are very faster, and it can handle large volumes of data. Clustering is done on customers. And if you take a bank would probably have 100 million customers. That's like 10 crores customers. 10 crores is huge data. And for 10 crore customers, if you have 100 variables, very much possible. I have seen 500 variables also when we really work on data science projects in real world. So 10 crore records by 100 variables is a huge amount of data, and any computations on that large volumes of data is going to be very, very memory intensive in the first place, and at the same time CPU intensive. Now, why k-means is so efficient? We are computing the distance based on the value of k. If it is k is equal to 3, it is 3 clusters versus 10 crore observations that you have. So that is 3 into 10, 30 crore computations are happening behind the scenes. In other algorithms, it is n by n computations. If you take hierarchical, it is computing the distance from each observation with rest of the observation. So the number of computations that you are going to do is n square, and the complexity to compute n square computations versus here k into n is many times smaller, and that's the reason in the industry k-means is chosen. To compute all of this, you need to have powerful machines, especially in production. If you have crores of observations, your machines should be probably having 64 cores CPU, and your RAM should be at least maybe like 512 GB. I'm not talking about hard disk, I'm talking about RAM. 1 TB RAMs, 512 GB RAMs are required to do those type of computations. And increasing the capacity of a machine is very expensive. So if you say 512 GB RAM is not good enough, can you get a machine with 1 TB RAM? Yeah, it would probably cost another $25 million to the company. That's a huge, huge amount of money, right? So you have to limit with whatever the infrastructure resources that are available with you. So when you choose an algorithm, we have to look at both. What is good about that algorithm? That's very important. Can it do it? Can it do our job? It can. Second, how is the infrastructure load if we use that particular algorithm? We need an algorithm which is light. If you take an algorithm, for example, in databases, you see this problem. A lot of people ask, we have so many different sorting techniques. Why have so many sorting techniques? Why have bubble sort? Why have other types of sorts, etc.? To sort the data, you probably have to have a very large array created in your real-time memory RAM and start populating it. And the sorting technique that you are going to use will decide what would be the size of your array on RAM. Just because one sorting technique is easy, if you start using it, you would probably want a memory which is 10 times the regular memory that you need. So it is going to be infrastructure wise very cost, very expensive. So you would probably not be able to use that algorithm to sort the data. Same thing with even data science algorithms. They are very heavy, computationally very heavy. So to keep the computations to as minimum as possible, you choose those algorithms which would try to do the job with less number of computations. Okay, hope that answers your question. Now let's move to the exercise. Import pandas as PD, import numpy as np from sklearn.cluster import k-means. What else I want? Okay, I think for now that's all. Let's start with the data. Empty. I'm going to use the same empty cars. pd dot read underscore csv empty cars dot csv empty cars dot head, so that you can look at the data. Oh yeah, we need normalization, right? From sklearn.pre-processing import min-max scale. Okay, that should do the job. So two things. Luckily, in this data, we all have numeric. So no need to check, no need to do any type of dummy variables or one-hot encoding. But if you have character data, we certainly have to do the one-hot encoding, converting character data to numeric in the first place. Okay. Second, are there any null values? I think we have checked this already using is null dot sum. So no null values. If there are any null values, we need to impute them. Let's try to scale it up. Now scale is equal to min max, what was the name, min max underscore scale. I don't think this is the right one, so let me choose. There are many types of scalars. Yeah, this one. This is the right one. because it's easy. You can use that min-max scale also, but I'm not going to use this min-max scale. I'm going to use this min-max scalar. Too many options, so it's difficult for us, even after working for so much on this. It would be um, difficult to remember all the operations, all the options that are available. So we are going to scale it dot fit underscore transform of empty cars. Not defined. We haven't executed this after adding that step. Now look at the data empty cars underscore scale. Okay, we have got scaled data, but unfortunately the scaled data is in the form of a array, not in the form of a data frame. We can convert this to data frame, not a big deal. Empty cars underscore scale underscore data frame is equal to pd dot data frame of empty cars underscore scale, comma, columns is equal to empty cars dot columns, comma, index is equal to empty cars dot index. Now empty cars underscore scale underscore df. Look at how clean the data looks like now. Data is always on the same scale. See here, 21, 160, WT, horsepower is on scale of 110, and some of them are zeros, ones, etc. After we scaled it and converted back to a data frame, it is very, very clean. Dot head, it's always good to print only a few observations. Okay, and this is also in the form of an array. So let's say we print 1 to 10 instead of printing all of them. Okay, yeah, looks like we have a couple of questions. It's not about complex calculations. Okay, I'll tell you how normalization is going to affect the data. Let's say we have points like this. So this is your years of experience, and this is your salary. So there is someone with let's say 5 years of experience, and they have a salary of, let's say, 20 lakhs. So this is 20 lakhs. So that observation is here. 5 years of experience, 20 lakhs. So we can write this as 5, 20. Now there is another person who is having same salary and having a years of experience of 10 years. So this is 10, 20, but 20 is in lakhs actually. So this is the actual data, and here it is also 20. There is 5 years of experience, and someone is having a salary of 19 lakhs 88,000. Now, if pictorially you see, there is very negligible difference between these two, and there is some good amount of difference between these two. Okay, but let's compute it. Now for this observation, this is 20 lakhs minus 20 lakhs, which is 0, plus what is the difference between years of experience? 10 minus 5 whole square, which is going to be root over 25, 5. So the distance here in this case is 5. Let us look at this distance. This distance is 19 lakhs 88,000 minus 20 lakhs, which is going to be roughly around 12,000 square, plus years of experience is same, 5 minus 5 whole square. So this is 12,000. Pictorially, if you see, these two observations are damn close to each other. Than this, for this it says the distance is 5, for this it says the distance is almost like 12,000. The reason is years of experience is on a small scale, so this equation gives negligible importance to the difference in years of experience, but very high importance to this salary because that's on a bigger scale. These two observations, someone with 5 years of experience having 20 lakhs as salary, someone with 10 years of experience having 20 lakhs as salary, there is a huge difference between these two people. Now that has to be accounted into the picture. How can we account that into the picture? If we take the scale of the variables out. Now if we, let's say, take the scale out, 5 years experience is 0.5 and 20 lakh salary is, let's say, 0.2. So this observation is 0.5 comma 0.2. Another one who is 5 years of experience, 10 years of experience. So 10 years of experience is going to be somewhat close to 1 comma 0.2. Now you can see the difference between these two, and for these two who is having 5 years of experience, X is going to be 0.5 and salary is also pretty close, so it's going to be 0.2. Now these two observations look very close to each other than these two observations. So that's the importance of scaling. Okay, I hope that answers your question on scaling. Now we have these ready, we have scaled data ready. Now let's try to compute the k-means cluster. We call this as Km is equal to, what is the k-means? K-means number of clusters. That's very important, right? We are, let's say we start with 3 clusters. Now Km dot fit, and what is the data that we have? This one. Sorry. So we have ran it and we have Km dot labels. So now if you run the labels, Km dot labels, it will try to print you the label for each cluster. So now I'm going to attach this to the original data set, empty cars cluster is equal to Km dot labels underscore empty cars dot head. So now we have attached a new column, each observation which cluster they belong to, empty cars dot cluster dot value underscore counts would tell you we have very less number of observations here. Cluster number 1 has 14 observations, cluster number 0 has 12 observations, and cluster number 2 has 6 observations. Okay, so simple steps. We started with k is equal to 3 and we fit the k-means on the scaled data. For each observation that we give as input, it has generated the label for each one of them. Now we are joining that label back to that original data set. We know which observation, which cluster they belong to. So that's how you get clusters. Next step, we haven't still figured out what is the ideal number of clusters to go with. Is it 2? Is it 3? Is it 4? So we have to do some sort of iterations to figure out what is the ideal number of clusters to go with. Then based on that, we can, based on the spree graph, we can decide what's the good number of clusters to choose from. Okay, there was a question saying how anyone's experience can matter with the amount of knowledge the person will have. A fresher can also perform well and maybe better than a experienced person. Got it. I do understand. The reason I am using this salary and years of experience is to just give you a view of how we can call two people as similar. What is the similarity between them? I am not trying to quantify who is a better person, who is going to perform well, who is not going to perform well. Okay. Having said that, if you think on the lines of years of experience, and if you want to make a judgment like this, when you look at a person, you look at them in two ways. One, we call it as the technical skill. Two, we call it as the interpersonal skill. So an experienced professional is valued both on the technical skill and as well as the interpersonal skill. At some point in time, when you look at the employees, the interpersonal skill becomes more important than the technical skill itself. It depends upon the role, what they are actually performing. Fine. Let's say I have an AI startup. I came up with an AI startup. There is a person who just maybe completed PhD in some computational analytics, came out of the college, very super talented, technically excellent, strong enough. Now, can I take this guy and put him or her as the CEO of my AI startup? You can, but you are taking a huge risk. Why? The role of a CEO is not just to understand the technical depth of the product. The role of a CEO is probably much more than what we simply see from the view of it. Like they have to handle the investors, they have to convince the investors, they have to get money from the investor, they have to manage this very well with the help of a lot of other people in the organization. Now, coming from a background of PhD, having a PhD in the computational analytics, doesn't really make this person to thrive well on that particular job, right? Technically, yes, I do agree this person is strong. This person could be the best person to lead a AI-based startup. But interpersonal wise, competency wise, this person is still immature to deal with a lot of stakeholders, to deal with a lot of different people. So in an organization, when you are looking at comparing the employees, you should not compare them just blindly on their technical capabilities. Second, for a person who is a fresher, you probably have to give a lot of instructions. Though they are technically capable, they haven't seen a full-fledged project by themselves. So in a full-fledged project, there is a lot of tough decisions that we have to make at different stages of the project. Now, this particular person who is a fresh grad, technically very strong, can do most of the complex programming, can handle most of the complex tasks easily, has to be still guided by someone who can take that decisions, who can own that responsibility. If that decision fail, though that person is going to take the blame, not the person who is trying to execute it, right? So don't think that I am comparing them only based on the salary or the years of experience. I'm just using them as pseudo examples here to tell you how you can call two people similar or two people different. I am by no means saying that by just looking at the salary and the years of experience, you could call a person same or you could call a person different. That's a pseudo example that we are using. So when it comes to the industry, when you look at the industry, when you have to look at the similarity of people working in the industry, you need to look at them in multiple dimensions. Like someone who has a PhD is technically more capable, no doubt about it. But someone who has worked in the industry for 10 years has a lot more decision making power and probably the strength to face those critical steps in the project than someone who is just about to start their career. Okay, I can give you another example because this is an unfair comparison. A lot of people do that. If there is a doctor who has specialization in maybe a heart surgery, he's a surgeon, but this particular doctor has just completed the course and about to start the practice. Now, having completed this doctor course and just starting that surgeon or starting a surgery, though the doctor knows everything what needs to be done in a surgery, probably the doctor did not face different types of complexity yet. Like how would the patient vitals behave if the patient is a blood pressure patient, if the patient is diabetic, if the patient has some sort of kidney problems, if the patient has some sort of lung complexities, right? You don't see such type of complexities when you try to learn from in a college environment. But the practical environment always throws multiple challenges at you. Everybody is a patient, but the complexity of the patient would be very different. Someone who has some sort of lung complexities, some sort of renal complexities, and having a blood pressure and being diabetic could behave very different under anesthesia, under different types of life-saving systems than someone who doesn't have all of this. Now, this person who has just completed that course of a surgeon and trying to start practice don't know how to handle that complexity. What type of different decisions they have to take when they hit these complexities. So that's why you probably don't put the patient to someone who is just starting the practice. You would probably have that person and another very experienced surgeon to coach this person on what decisions need to be made at different steps so that eventually it is going to be successful. Okay, that's a fair comparison. But just for the sake of explaining it here, I'm using them as pseudo examples. Okay, don't take by heart that I'm trying to compare the people only by their years of experience and their salary and say years of experience is nothing. It is almost negligible. You should never be saying that. everything has value. Fine. Let's complete that one last step of creating the clusters by running them in a loop and try to generate the different values of the sum of squares. I'm not going, because we only have a very few minutes. I cannot type that code one by one. I'm just going to copy paste the code here and make some changes to it. Km.fit, and here we need to give our scaled data. So this is our scaled data. Okay, this function needs to be created. Let's create that function. You would not have to go through all of this at the beginning, but just for the sake of decision making, I want to show you how does that plot look like, and let me quickly complete that. So this is the plot that I was talking about. What we did is we computed the clusters by putting it in a loop ranging from 2 to 15. And every time we generated clusters 2, clusters 3, clusters 4, all the way up to clusters 15, we took the value something called as WSS, which is called as within sum of squares. You would not be understanding these two unless you understand some basic statistics and how we compute them. So that's why I'm not going to deep dive into those metrics as of now. Look at the graph. When the clusters is 2, the number of within sum of squares is 20. To 3, it decreased to 12.5. With 4, it came to 7.5, and with 5, it came to, let's say, 5, and after that, it almost has got flattened out. So maybe in this case, we could say we could go with 5 as the number of clusters. So our number of clusters is equal to 5 km dot fit on the scaled data empty cars comma scale df. You got the labels km dot labels. Let's try to attach these labels to the empty cars data set again. Cluster is equal to km dot empty cars dot cluster dot value underscore counts. Sorry, now we have generated 5 clusters 0, 1, 2, 3, 4. So in cluster 0 we have 7 observations, cluster 1 we have 12, cluster 2 we have 7, cluster 4 we have 4, and cluster 3 we have only 2 observations. Okay, and when we looked at this free graph, we decided that this is the ideal number of clusters to go with. Okay, that's exactly what we do in k-means, and I hope you have a good amount of. In k-means function, you have two most important parameters. One, which is the number of clusters is equal to 5. So you have to decide the number of clusters. And in the computations, we generally have something called as initialization is equal to k-means plus plus. So this is how the centroids are going to get initialized. Don't change this. Keep this to k-means plus plus itself. And rest of them are all optional. So if you want more details about what each of these things are going to perform, always take the help from the Python. So clusters, default is 8. If you don't give the number of clusters, it would be computing 8 clusters. Initialization, there are two methods, initialization methods. K means plus plus, the other one is the random method. So initialization can take one of this, either it can take this string here or this string, only these two, right? So what k means plus plus does and what random does, selects initial clusters for the k-mean clustering in a smart way to speed up the convergence. So it tries to compute the means of each of those observations that we have and try to do a percentile based selection. So the convergence would be faster with if you choose the initialization k means plus plus. So that's why I said don't change it. If you go with random, no pre-computations will be done. It randomly chooses k observations, k centroids to start with. So you don't have to rely on understanding these arguments by reading through it. You just take the help. It would give you complete clear-cut explanation of each and everything that is built into the Python function. Okay, we have 15 more minutes and I want to spend this 15 more minutes to give some guidance into further reading and also some kind of more information about AI, because a lot of people has been talking about AI and asking about AI since from the beginning. To start with, machine learning is a very huge subject by itself. There are a lot of things that you have to understand in machine learning and understand in the concepts of ML before we touch any type of artificial intelligence. So within ML, you have to understand these things. First, ensemble techniques. So without understanding ensemble techniques, you don't really see the power of ML. So the power of ML comes in when you understand this ensemble techniques. Second one, you have to understand the concepts of something called as decomposition. So we call this as data decomposition. Data decomposition can be done by principal component analysis, singular value decomposition, LSI, a lot of different techniques. So you need to understand what really PCA does, what SVD does, etc., to understand the advanced concepts. And within ML, you also have to understand the lot of similarity functions. Like I said, we have a different types of similarity functions. So to understand this, you can read about how can we build recommender systems. This is one of the biggest applications of machine learning, building recommender systems. And finally, you start with support vector machines, how support vector machines work. Someone asked about an example of support vector classifier. Unfortunately, I don't have time to give you an example of support vector classifier as part of this. But if you start with SVM, that's where you would probably come across a support vector classifier. And then you have to understand neural networks. Somewhere in between, to understand these concepts, you have to understand statistics, and you also have to refresh your concepts of probability, especially in linear algebra, matrix manipulation. How do we compute matrix manipulation? So if you are familiar with this, then comes the most advanced topics in AI, which starts with neural networks. It's all about neural networks. Different types of neural networks are used in AI. So AI, all the techniques that are used in AI starts with the concepts of neural networks. But to understand them, you have to understand all of these concepts in ML. So without understanding this, if you directly jump into AI, there is no point. It's like trying to learn swimming in a river, which is practically impossible, right? So in AI, you have two types. One, the deep learning, which is the technicalities of it. In deep learning, you have something called as convolution neural networks, recurrent neural networks, um, generative adverse networks, and then you have within RNN you have some things like LSTMs, etc. So the more you try to read about it, they will become more and more complex. And when it comes to applications, a lot of people only focus on the application side of it. They don't focus on the technicality side of it. So if you have to understand how AI really works in principle, you have to understand all of these, how they actually work, right? Reinforcement learning. So these are very important for anybody to start learning AI. But on the application side, you have computer vision, you have image recognition, you have natural language processing, you have linguistic models, which is generally used for language constructions, etc. You have speech recognition and people talking about self-driving cars, etc. They fall mostly into this computer vision-based models, right? A lot of people are still talking AI at the application layer, like what application they are trying to build. Are they trying to build a computer vision based one or image recognition one, or using natural language processing, using language models for language conversions, etc. But how they work behind the scenes comes from the concepts of your deep learning. And how deep learning works comes from the concepts of neural networks. So there is a hierarchy to it. So if you learn this, then you go to your neural networks, then you go to your deep learning algorithms, and building application of is using these deep learning methods is what going to be the highest form of AI. And it's a journey. Nobody can become a AI practitioner in a month or two. It takes a lot of time, and it has to start somewhere. It has to start at the understanding of machine learning techniques. Once you are very clear with these concepts of not only the other concepts that I have explained so far, you have to understand how ensemble techniques work, how different types of decomposition work, how we can try to measure observations and their similarities, some sort of advanced machine learning like support vector machines, neural networks, etc. This will set the foundation for anybody to even think about becoming an AI practitioner. Having said that, there are a lot of inbuilt APIs. Google has built APIs, Apple has built APIs, Facebook has built APIs, right? Now, a lot of people that you see is using an API built by Google or built by Apple. To that API, they give some pictures and it will try to learn and it would start predicting, it would start to identify faces from it, right? So that's also okay, but they have limitations. You haven't trained them. How they work, you don't understand. These are pre-built APIs. You can also use them to build some of simple applications, but to get thorough knowledge on AI, you probably have to understand the concept of these things: CNN, RNN, GAN, and reinforcement learning. So only if you understand these concepts well, Then the applications that you are going to build out of your AI, based on AI, are the ones which are going to be complete. And these are the typical applications that we are building using AI these days. You can do this a lot for weather forecasting, for some sort of stock market forecasting also, but the basics has to start from this. The concepts has to start from this. Okay, so that's the guidance about how you have to start or phase out your career slowly. Most of you, I understand, are students who are in maybe second year or third year mostly, and you still have a lot of time. Of course, you have to focus on your curriculum first. Along with your curriculum, if you can pick up some of these concepts way ahead, by the time you complete your undergraduation or post graduation, you probably have learned half of these basic concepts that are required, so you can easily thrive in this field coming out of your college, coming out of your school. So that's going to be very effective way of learning data science and becoming a data scientist or a AI practitioner. I wish I have done justice to the 10 hours that was given to me, and I hope most of you might have got at least some very basic understanding of what data science is, what AI is with this 10-hour workshop. um, Please continue your learning, and um, it is always going to be a lengthier journey learning data science. It's not like you do it in a month or two. So start it, be slow, learn one by one at a time with this basic knowledge, with this basic knowledge of how different things work. As you start learning, apply them on practicing with some simple examples. There is a tons of things that are available on the internet. You probably need a little guidance. You try to get that guidance once in a while from someone who can coach you. I wish all of you good luck. And with that, I think I have completed what I had as my agenda for the workshop. I really enjoyed the discussion and all those questions that you guys have been posting on the chat. And I always love interaction with people. Interaction is the best way of learning. All of you have a great time ahead.